So my name is Patrick Conrad. I'm a flight software engineer at SpaceX. I've been at SpaceX for 2 years, and I'm a member of the simulation team.
My name is Matt Sachtler. I'm also a flight software engineer at SpaceX, coming from the vehicle side. So I've worked on Falcon and Dragon. Most of my career at SpaceX has been spent as the lead technical person on the Falcon software team until recently, when I kind of moved over to go work on Bazel stuff. But yeah, I'm going to let Patrick give the overview, then I'll hop in a little bit later on.
Yeah. So over the last year, we have been converting 2 of our major build systems over to be done with Bazel instead. And essentially, what we're going to do today is tell the story of that work. So I'm going to start off by giving an overview of SpaceX and software at SpaceX with a lot of gratuitous pictures of rockets. And then we're going to talk a little bit about why we found ourselves wanting to make the conversion to Bazel. And then I'm going to hand it over to Matt, and he's going to give you details about some of what that process looked like for us, some of what we learned along the way, and some of what we're trying to go do with this in the future. So most of you probably know who SpaceX is. We are a rocket company. We were founded in 2002, which actually lines up fairly nicely with the history of the Bazel. And our goal is to revolutionize the access to space and to bring rocket costs down dramatically and ultimately to make humans an interplanetary species. Since then, the company has grown a lot, and that's going to be an important part of our story. The fleet that we fly today is principally the Falcon 9 rocket, which we use for all of our launches, and the Dragon space capsule, which flies cargo, food, supplies, and science equipment to the International Space Station. All that's done under contract to NASA. And one of the really interesting parts about Dragon is that it can not only take stuff up, but it can bring science equipment back down for later study on the ground. And from NASA's perspective, that's a really important capability. I also have a picture here of Falcon Heavy, which is should soon become the newest addition to our fleet. So instead of having a single first stage, you have 3 first stages, which dramatically increases the amount of cargo that you can lift. This should should fly fairly soon. And the scale of this thing is incredible, and we are really excited to see this thing fly. It's been a long time coming, as anybody who follows SpaceX knows. From a software perspective, something that's very interesting is that the Falcon and Dragon vehicles are very different. One is a rocket, one is a spacecraft. But from a software standpoint, they share an enormous amount of common infrastructure, and they're built from a common code base. So the next thing I want to do is put up a recap of one of the most recent Dragon missions. But the thing I want you to watch for as we go through the video is that everything that you see, everything that the rocket does, there was software involved in making that happen. So during launch and power descent, the vehicle is processing a very large amount of data in order to make control decisions, to steer the vehicle, to look for faults, and otherwise do everything required to maintain stable flight. You have the moment of separation of the first stage and the second stage, which is this really interesting moment because you go from having one vehicle to having 2 distinct vehicles. The first stage executed a flip to head back towards the launch site, and executes a re-entry burn to slow the descent through the atmosphere, enters most of the atmosphere under control of the grid fins, which are up at the top, establishes itself over the landing pad, executes the landing burn, deploys the legs, and comes down for a soft touchdown, and our entire building cheers when this happens, still to this day. And then you have the deployment of Dragon, and so now Dragon is in free flight, deploys its solar panels, has power generation, and is now well on its way to the International Space Station. The biggest story for the company this year has been scale and reusability. To date, we've had 19 missions where the first stage successfully landed on land, and I'm sure everybody has probably seen some of the footage that we've gotten from that. And then 3 of those missions were actually ones where the first stage had already flown previously, and all of those were recovered again successfully for the second time. Probably the lesser known story about reusability for us is that we've also reflown a Dragon capsule for the first time. That happened earlier this year. And so one of the founding missions of the company was that if you don't have to build a new rocket every time, space travel would be a whole lot cheaper. And this year has really started to show the reality of that vision. Looking forward, one of the major development efforts at SpaceX is the Dragon 2 space capsule. This is being developed under the Commercial Crew Program under contract to NASA. So this is going to return to the United States the ability to launch our own astronauts into space. From a software perspective, there are a whole bunch of interesting challenges that come when you actually have to fly people inside the vehicle. And it's clear that when you watch videos of our launches, we have a mission control. There's a lot of user interfaces that we have to build to support the ground side operations and all the operators. But when you have astronauts inside the capsule, they have interfaces that they will need. And so we have an entirely new team that's building the kinds of interfaces that the astronauts will need. And you have to deal with things like having interfaces that work when you're in gloves for a spacesuit and other kinds of related problems that are very different than what happens when you have people at consoles in a mission control setting. Looking further forward, the company has begun talking about our plans for Mars, and this is something also that the software organization is beginning to think about. So if this is all the really cool stuff we get to do at SpaceX, I have to give the disclaimer that unfortunately, the kind of technology that we work on is heavily regulated by the United States government. So contributions to an open source project like this are difficult for us. We have to do a lot of legal vetting that we're not revealing things that are regulated. But we are here, we are trying to participate in this community as best we can. We do have a GitHub page, and Matt has been posting to the Bazel project using the handle that I have here. It also means that today we're not going to be taking any questions from the stage, but we will be here and we would welcome questions. We'll do our best to tell you as much as we can. So SpaceX, I think, is best known for our rockets. But as I mentioned earlier, everything that happens on the vehicle has software that's involved with it. And so we actually have a significant software organization that builds the tools that we need to design and operate and run these vehicles. And so I want to give a little bit of a picture of what that's like. So aerospace systems, modern aerospace systems are very complicated. And they have a lot of very, very highly integrated systems. So that not only means that you have the structure, you have the metal of the vehicle, and you have integration with the propulsion systems and with the avionics, but also the hardware is built to be controlled by our software, and our software has architectural decisions that go with the hardware that it's intended to fly on. And that means that our flight software engineers have to understand in great detail the physics of the problem and how the vehicle is actually built and how the hardware will respond to the actual situations. These systems are incredibly expensive, not only in terms of the financial aspect that the rockets themselves are expensive and the payloads that we fly for customers are expensive, but whenever we have astronauts involved, these are life safety critical systems. And that adds a lot of challenges and a lot of rigor to our process that we always have to be concerned about. The basic idea then is that you have to understand as much of these systems as you possibly can. And then that is the only way to design and build them safely and to operate them as intended. Now, in the software world, everyone knows that you have to have staging environments to test your software in that are as much like your production system as you can. But when your production environment is being a rocket flying at thousands of meters per second, that adds a whole bunch of interesting challenges. So the aerospace world in general has a phrase for this, is that you have to test like you fly. And a huge portion of the company is based around, in all of the different aspects of the rocket that we build and the software that we fly, of executing the idea that you have to test like you fly. And again, that means you have to understand the system very, very well. So we have a significant test organization that, again, has to understand not only the software, but also all of the hardware that it goes on to understand all of the couplings between those systems that they need to go test for. So they're not just looking for software bugs, they're looking for problems that will cause the mission to fail. It also means that some of our test environments have to include hardware because the hardware and the software are highly coupled. So you have to see that the joint system works correctly. And then that also, so there's just an enormous amount of energy trying to have flight-like environments on the ground. And so that actually brings me to the two repositories that we've actually been working on the build systems for. So the first is the one that my team produces, which is the simulators. We have high-fidelity physics simulations of all of our vehicles that we use to analyze and design and test the rockets that we build. And then we have the rocket repository, which has all of the control software for Falcon and for Dragon, a whole bunch of the ground support equipment. So the basic workflow then is that we do analysis in the simulation environment. We use that to figure out what software we should write. We go over to the rocket side, you write the production flight software, and then you play the two against each other in a test environment to make sure that you've actually written the software that you wanted. These repositories are fairly significant. They're each 1 million lines of C++. And then, of course, they have the collection of scripts and tests and shell scripts and a bunch of Python that you need to pull together large functioning repositories like this. The simulators run on commodity Linux desktops and servers. And so from a build environment, they're relatively straightforward. But the rocket side of things is more complicated because this is embedded software. It has to run on, be compiled for, and then run on the collection of environments that we fly. So I've got this little box here that says we have lots of platforms, but it turns out we have a team of people whose job is to create the Linux flavor that we fly on our vehicles, to make sure that it's configured correctly, and to provide us libraries and tool chains and everything that we need to have a stable, really well understood environment to run the rocket software on. And so when you take all of this together, the size of the repositories, the complexity of the test suites, and all of the complexity of the run platforms, the build systems for these two repositories end up being fairly complicated. So when you look back at the history of the company, the build systems for these two repositories go back to the very beginning. And these are actually two of the very oldest repositories in the entire company. The build systems have grown and evolved with us over the years through enormous increases in the number of developers, in the size and complexity of our code base, and also in the scale of our continuous integration systems, which, by the way, got forked from just somebody wrote a script to run the build to now we have an entire team that manages our continuous integration, our data analysis systems, all of our deployment tools, all that kind of stuff. There's a lot of complexity that has built up over the years. But we were still finding that the make system that we had built was letting us down. And in particular, you have users who are finding themselves just needing to get their daily work done and their development tasks, and they're fighting the system or working around it. And so we needed something to do better. So we started looking around fairly widely at what we might do to go improve the situation. And it pretty quickly became apparent that we were not looking at a small bug fix. We at least needed to think about maybe doing a big rewrite or a rewrite from scratch. We looked at a whole bunch of technology platforms that we could use to try to build the solution. And obviously, because we're here today, we ended up choosing Bazel as the platform that we were going to use. And the key for us here was the quality of the dependency tracking that Bazel provides. Because when we look at our ecosystems, they are absolutely full of dependency tracking problems, far beyond just the need to take your source code and compile it into executables. Because you have tests that examine certain parts of the code. You have data that are ingested by those tests. You have to take configuration data and binaries and package them up into artifacts to be deployed onto targets. And then the list goes on and on. So as we look forward, there's a whole bunch of problems that we're hoping to solve with Bazel. And to our mind, there are two really key things about Bazel's approach to dependency tracking. The first is sandboxing, because it's really hard to replace the active enforcement mechanism that each of the build steps that you have described are what you have said they will be. Because the sandboxing ensures that it just won't work if you haven't done that correctly. The second part is that you can get all the way towards full reproducibility, which is very hard to do in a lot of other systems. But that gives you an actual property of your build that you can check at the end. And when you put those two things together, to our mind, it gives you an unparalleled ability to trust the foundation of the build, that it is what you said, and to use that to go provide a reliable platform that you can go build a bunch of really cool things like the incremental and network builds that we heard about earlier. And so looking forward, we are hoping to use Bazel as a platform to go solve a bunch of these problems and to take advantage of the strength of this platform, also to provide a common tool architecture. Now, that's getting ahead of ourselves a little bit. So at this point, we've now decided that we're going to make this conversion to Bazel. We haven't actually done any of that yet. And so this is where I'm going to hand things over to Matt, and he's going to tell you more about the story from here.
All right, you guys hear me okay? All right, cool. So we started this whole effort in 2016. It was just about a year ago, a little over a year ago. And as we were realizing that we had this sort of big dependency tracking problem and that we wanted to make some big changes, we were discussing this amongst a bunch of us, and we had someone on our team at the time who was an ex-Google employee who his advice to us was basically, if you're going to go through all this work to go build something, replace the build system, whatever you choose, you should take a serious look at Bazel because they've thought about all the things that you're going to end up thinking about, and they've made a lot of good decisions. So make sure you at least understand what Bazel did before you go and do anything else. We took a look at it. He was right. And we spent a little bit of time doing some Hello World, sort of get our hands dirty with it, understand what the tool was about. And about a month later, we made the first pitch to the rest of the team that, hey, we think this is probably a good idea. We think it's worth spending some time doing a port of our build systems over. So the conversation at that point was really about how are we going to show that we did a good job at the end of it, and how are we going to maintain this system later on? That was the primary thing people were interested in. So that was a conversation we were having very early on. I'll talk a bit more about that later. So we spent a couple months doing some sort of demo ports of both the repositories. So Patrick started in the sim repo, did a little bit of work to show, hey, I did a thing. I took that, took it a little bit further. We kind of went back and forth across the two repositories, sharing what we learned and taking the fidelity further and further until we got to the point where pretty much everything worked. There was a notable exception to that we sort of misestimated, which I'll mention in a couple slides. But we got to the point where we felt confident that, yeah, okay, we think we can commit to this. So in March of this year was when we kind of set the demos aside and said, okay, we're going to do this for real. We're going to code review everything, go through testing, and get it committed. And finally, just about a month ago is when we did the real cutover to production of using Bazel as the primary build system. So a bunch of aspects of this. A lot of the things I'm going to talk about are going to sound very familiar from what we heard this morning, which is actually really encouraging to me. So let's get into it. So our first party code, all the application code across both repositories. The overall philosophy here is we're building the system out in parallel, and we want to do that as fast as we can so we can get rid of the old one and go take advantage of all the benefits that Bazel has brought us. So we're trying not to get bogged down in making improvements along the way, just get to the point where it works and it's done, and then we can go start using all the great tools at our disposal. So all the application code, it was really the core Bazel workflow. We've got a bunch of files that are laid out in a fairly regular pattern, collect those up, pick your flags, define your libraries and your tests, map to the data. All that stuff was pretty straightforward. The key thing here, though, was relearning all of the little things that our old system had grown over 15 plus years of existence. Turns out you accumulate a lot of little features and things that way. We had to go find all of those and go find ways to re-implement them in Bazel. But this was relatively successful. As Patrick mentioned, we have a lot of different targets that we build for. We have an entire team of people working on maintaining those compilers and the sysroots and headers and all that stuff. And that changes fairly frequently. We also control the whole thing, and we build our own compilers and manage them all the way to the OS that we run on the hardware. So at build time, we need to know which compiler am I using right now, where does it live, and how do I actually invoke that compiler. We had this problem before moving to Bazel, though. So we had a lot of infrastructure that was built up around the old system to let us answer these questions and go and kick off builds. So the problem for our tool chains was really about teaching Bazel about that existing infrastructure and sort of extending it out into Bazel, which took the form of two things. First, the cross-tool files, which was, as we did our first demo of this and we're trying to figure out how cross-compilation worked, ran very quickly into the end of the documentation about this and got to go do some spelunking. Learned a lot in the process. And the cool thing was that everything we wanted to do, we could actually express with the cross-tool file. That was a really good confidence building step. They're like, oh, hey, they actually thought about all the things that are important here. Didn't write it down, but they thought about it. The other piece then is the command line flags to go and choose which of the tool chains we're building with. So relatively straightforward story once you kind of wrap your head around the cross-tool files. The last big piece of this was the third-party code, and there was a little bit of discussion about this earlier. So there are at most maybe 2.5 of us working on this effort at any given time, sort of on a good week. So we didn't have a ton of staff to go and write build files for all of our third-party libraries, and we don't have a ton of them. There's a handful that range from fairly simple, where it's actually feasible to do that, to a couple of very complicated third-party libraries. So we didn't think it was feasible for us to maintain build files for everything. We also considered maybe we just build them once, commit the results, and just wrap that with the CC libraries. Problem is that our tool chains are evolving and moving so quickly that we thought we'd end up recompiling these things pretty frequently. So we went the route of implementing a Skylark rule that wrapped a shell script that invoked that build. The simple version of this is pretty easy to get working early on. You can almost just use a gen rule to do that. We ended up going a little bit more fancy than that. But most of the work here was really around trying to get it to the point where it was actually fully reproducible. We see all the advantages that come if we get to the point where we get completely reproducible builds end to end. So we really wanted to get there with this approach. So the challenge here was really about learning all of the little things that Bazel has accumulated over its long history to do this job well for C++ compilation. And we re-implemented a lot of that logic ourselves, which it was a bit challenging at times, but we got to the point where it works. All the libraries that we're building right now are fully reproducible, which is great. At the end of that process, we get like a .a file and a couple headers. We can pull those out and then pass those downstream. So that leads to the validation story. As I mentioned, we were talking about this early on with the rest of the team and how we were going to show that everything is good and correct. Most of this process takes kind of the form you'd expect to build everything, run all the tests, run it in the staging environment, get happy with it. We tried to get that part of it working as soon as we could so we could get it running in CI. Once we had gotten to the point where we had a mature enough build that we could get it running continuously, then we could watch to see that it's, the new build is passing when the old build passes. The new build fails whenever the old build fails. We had a case where that actually wasn't true. I'll talk about the specifics of that in a couple slides here. But that was a big like, oh, wow, this is actually a really important thing. I'm glad we got to this point as early as we did. So pushing to the point where we had CI running was a big part of the focus and the planning of this. For Sims, that was about as far as we took it. Once we got it in CI, all the tests are passing. It's a pretty good place. But for the rocket repository, because this is the code that we're putting onto our rockets and spacecraft, we wanted to go to another level of showing that what we had done was correct and equivalent to the system we had before. So we realized that, okay, we have the tooling at our disposal to build all the different configurations we care about. Let's go pull all the flags out of every command line that got invoked in both systems and try to figure out if they were doing the same thing. 1 million lines of code, it's a pretty big repository. There's a lot of flags involved with this. I don't have the number of build steps off the top of my head, but a pretty big pile of command lines. So there's some scripting involved with doing this. It was relatively awful, but we got to the point eventually where we were able to convincingly say that, okay, we've looked at all of the flags used in the make system and all the flags used in the Bazel system. We understand all the differences. From there, we're building the same set of files with equivalent sets of flags. We would expect, at least at the compilation level, that all the object files produced would be the same, maybe minus debug symbols, so strip those out. And we tried this, and we were actually pretty close on the first try to getting fully matching object files across the two repositories. A couple places where we weren't, and we found more issues there, went and fixed those and got to the point where every single object file across the board lined up between the two systems. From a validation story, that feels pretty good. We know that Bazel is now compiling the code the exact same way that our previous system was. A couple of things that were new for us in the validation process. First off, determinism of the build is something that we hadn't really thought about previously. We're excited that we now have this property that the build will continue to be identical, but how do we show that that's the case? This is an area where we'd love to hear best practices of how to do this in CI going forward. Having spent a year with the tool, we think we have some ideas on how to do this, but it's the sort of thing that we'd love to hear from people who have thought about this problem for a lot longer than we have. Finally, the Bazel query is an awesome tool. Having structured access to the dependency graph is really cool for not only doing things like refactoring in the future, and like I said, we were trying to hold off on doing as much of the improvements of the code base as we could until we had ported over to Bazel. This is one of those reasons why. So if we want to go break up the code base and rearrange it and things like that, having the query give us structured access to that dependency graph is really, really great. The other aspect of this that we had a lot of conversations about is how do we get comfortable upgrading Bazel itself? We know the tool is going through a huge amount of development while we're going through this porting process. So how do we get comfortable that Bazel is doing the same thing as it was doing previously? And this is one piece of that, of being able to see that, okay, it has read all of our files and it's going to do, it's at least expressing the same dependency graph as it was before. Okay, so once we had gotten to the point where the validation finish line was like starting to materialize on the horizon, we're getting pretty far along, we started a rollout to the rest of our coworkers. So this was a phased rollout where we found a couple people who are willing to put up with the fact that it's probably broken and we haven't thought about some things and the documentation is not very good yet. Got them to the point where they were using it on a daily basis and kind of spread that group out and out and out. And our takeaway from this, now that we've had people using it, quite a few people using it for a couple months now, is primarily that the fast correct choose to tagline is very real. We've seen that over and over again, that it really has paid off. But there are some expectations that need to change. We came from Make. Pretty much everyone on our team either knows Make well or has expectations about the way that Make works. A couple examples of this. If you tell Make to build with, 50 jobs, it will happily try to go and run 50 jobs all the time. Whereas Bazel has a more sophisticated assessment of how much CPU and RAM and I/O do you have and schedule tests accordingly. The result of that is if you ask both systems to run all of your tests, it may take a little bit longer in Bazel, but you can keep using your workstation in the meantime in general. Whereas that definitely wasn't the case in the old system. So people would say, hey, it took longer to run the build. It's like, well, but you can use your machine. And also you don't have to run all the tests all the time. Now you can trust that you can only rebuild the tests that you care about. And the time savings there are huge. Another example of this that came up was removal of a header file. In the system we had built around Make, we were not nearly as careful as Bazel is about tracking all the potential theoretical ways that header file might have impacted some piece of code, which meant that if you did something like that, it's the type of scenario where you can end up with an invalid build for whatever reason. That can manifest itself in a lot of ways that result in make clean, blow it away, rebuild everything. People were very used to doing that in a number of different scenarios. And that has just disappeared from people's workflow now that we've ported over to Bazel, which is just really great. Can't understate how happy we are that part of the workflow is basically gone. Disk space usage being the one that remains, but that is what it is. Okay, a couple miscellaneous challenges. So the feature that we thought was going to be okay after we did our demo, but was very much not done at all, was C++ code coverage. We ran headfirst into that. The Envoy folks, it looked like, had done a similar journey that we ended up going through and posted that on the GitHub issue about this. We didn't really realize until we were almost done that we were doing exactly the same thing, but it turns out that it was pretty well documented there. So we spent a lot of time getting something working here, but it was a lot of climbing into Bazel itself and making some local modifications. So that was quite a bit of effort expended on that. Additionally, include paths for our C++ rules caused us a lot of pain. A lot of this was self-inflicted because of the way we've laid our repositories out, but also the CC library includes attribute I think when we started out, wasn't documented as well as it is now. We misunderstood what it was doing in using iSystem instead of -I. That was the root cause of the CI build that didn't break in both systems. Because it was using iSystem, it paved over some warnings in a header file and passed the build when it failed in the old system. Things like that have resulted in quite a bit of wasted time on our side. So that was, like I said, mostly self-inflicted, but it was actually a pretty recurring challenge. Python support is one where we don't have a ton of Python in these two repositories. We do have a lot of Python elsewhere around our team and around the company. Migrating from the very standard virtual environments and pip into Bazel, the story there is not super clear. We're hoping to learn more about that here at the conference. And then unit tests is another one where we had built up a fairly sophisticated test runner, but Bazel actually had much better tools in general for managing tests. The flaky tests in particular is a thing that we hadn't built that is really awesome. But we had never been in a situation where we needed to very carefully express the dependency between which tests need which data. So we have all of the data and all of the tests, and the dependencies are not really more fine-grained than that. It's going to take us a lot of effort to go and get to the point where we've then specified all those dependencies very carefully, which is a good problem to have, but it's going to be a lot of work for us. And finally, both Bazel and our own code base were moving targets during this entire effort. I had the version numbers on the sort of timeline slide. We started around the 0.4 range, and now being an 0.7, it's changed a lot in that interim time. So there's a lot of effort that went into keeping up to date and reading about issues. A lot of the time we had like, oh, we found a bug. Oh, wait, they fixed it 2 days ago and it's in the next release. Okay, just hold off. Happened several times. But also our own internal code bases were changing a lot during this time. We've had a lot of launches, a lot of new features being built, and a number of different features of the build that were introduced that we had to then go and chase. So each step of this was a huge learning opportunity for us, both about our own system, about how Bazel works, occasionally about how C++ compilation and linking actually really works down in the nitty-gritties. But we think it's likely that anyone who's going through a similar sort of porting process, a lot of C++ code, moving into Bazel is going to go through a pretty similar set of phases. We've already heard this morning about similar sorts of challenges. And we led this entire effort with that question, like, how are we going to show this is correct? That's, for us, we have a pretty high bar for that because we're building rockets and we take testing very seriously. But answering that question early on of like, what is our validation story around this was the first thing we talked about, and a constant question that we were discussing as we went. And that was a really key part of our success in doing this port. So looking forward, like we said, we've ported 2 repositories over. We have a lot more code to go and port elsewhere in the company. We also had, given that approach of go and replicate the old system in Bazel, we now have to go and take advantage of all that hard work. We held off on a lot of improvements that we wanted to make, and that is now available to us. We can do that freely without having to make updates in 2 systems simultaneously. So a couple things that are on our minds, particularly about what would help us. First 2 things straight off the roadmap, straight off the conference agenda here. Cross-platform multi-tool chain support. We're definitely a big use case there. We have a lot of different tool chains, a lot of different platforms. Luckily, not worrying about mobile devices or Windows or Mac. It's all Linux, but we do have a lot of CPU architectures. Remote caching and execution is going to be awesome when we are able to go incorporate that. So we're really excited to learn more about that. But furthermore, the general problem of building great CI, that's really the part of the conversation that got us started in this whole thing to begin with. And the problems we have here are definitely not unique. And so sharing of tools and methodologies on how to go and build CI that takes advantage of all the great things that Bazel provides is something we're really interested in. Furthermore, just general sharing of best practices. The documentation that exists is great for how to go do specific things with Bazel, but we have questions like, hey, we have a huge C++ repository that was built in Make that had its own quirks and things. Bazel has opinions about how to do this really well, and learning those and sort of teasing those out are the sorts of things that we'd love to hear more from people who have a lot of experience doing this. Third-party libraries, we talked about the thing we did. It sounds like there's a number of different approaches you can take there. In general, we don't know if the thing we did was a good idea or not. It seems to be working okay, but we definitely want to hear more about that problem space. Python rules has been mentioned a couple times already, but what the story is there, we have a pretty big pile of Python I'd like to go and port over into Bazel, knowing what to expect there around reproducibility and packaging and third-party libraries, all that stuff. And finally, just stories from all the rest of you. We spent a tremendous amount of time on Bazel Discuss and GitHub issues and Stack Overflow during this entire effort. And it's incredibly useful to hear what people are doing, what problems people are running into, approaches that are being taken, things like that. We really appreciate all of those stories that have been shared already and will continue to be in the future. So we're a year in. We've ported 2 repositories over. At this point, we're very much invested and committed in the tool. Every feature that is being built helps us write code faster, write code safer, and ultimately build more reliable systems. And that gets back to why we're here. We're not, we didn't start this effort just for the sake of building a build system. We're trying to build rockets and spacecraft. And SpaceX's mission is to dramatically accelerate and revolutionize humanity's access to space. And Bazel is helping us do that. All of you are helping us do that. And I think that's really great. Thank you.